I'm very happy today to present our recent work called On the Pauli Spectrum of QAC 0. This was done with some of my great collaborators, Shivam, Natalie, and Henry, all from Columbia University. We recently presented this work at QIP and will be presenting it again this summer at Stock. To start the talk, I just wanted to begin with a brief bit of motivation through a personal anecdote that kind of involves my own journey in research. So as an undergraduate, I was at MIT working in Professor William Oliver's lab, trying to build superconducting quantum computers. And during my time there, I learned that the goal of experimentalists is to build these large-scale, fault-tolerant superconducting quantum computers. But in reality, it's very hard to control even just a few qubits and protect them from noise. So all of this said, it seems like it'll be a while until we're able to realize these large-scale fault-tolerant quantum computers. And in the meantime, we'll have to deal with small, noisy systems with limited coherence times on which we can run short-scale computation. For my PhD, I moved to Berkeley and transitioned from experiment to theory. And so one of the first things I did at Berkeley, I went around Soda Hall and the Simons Institute, and I tried to ask classical computer scientists what they care about. And many of them told me they wanted to understand specifically bounded depth circuits, namely how they compute, what they can compute, and what they can't compute. And so naturally, given that we're in this NISQ era of quantum computers in which we really can only run short depth quantum computation, a natural question that quantum computer scientists should care about is what constant depth quantum circuits can and can't compute and how. And this is what my collaborators and I set out to assess in this work. So to give a high-level summary of what we studied and achieved in this work, we looked at these constant depth quantum circuits, and in terms of how they compute, we were able to show that they have low-degree Fourier spectrums. So if you're not too familiar with the notion of what I mean by a low-degree Fourier spectrum, an example of a function that has this property is the Junta function. I'll also elaborate on it more a bit later in the talk. In terms of what they can't compute, we were able to show that they can't compute high-degree functions. So a very important example that I will come back to later in this talk is the parity function. And in terms of what they can compute, we were able to show that we can efficiently learn what these constant depth circuits can compute. So this is really a high-level statement of what we did in this work, and I'll spend the rest of the talk really breaking down all three of these results and giving some technical background as to how we were able to prove them. I just wanted to, before diving into all of this, start off by saying that our result involved techniques from a number of disciplines. So it was really at the intersection of quantum computing, complexity, analysis of Boolean functions, and learning theory. So there's a lot of different techniques, ideas, and jargon going on here. When I started this project, I definitely wasn't an expert in all of these different areas. And throughout the course of this talk, I'll try and introduce all of the key components needed to build our result. But if I say anything that might not be familiar or I didn't explain too well, feel free to ask a question. Okay, so for the talk today, here is the roadmap that I was going to follow. I was going to begin by describing basically this seminal result from classical complexity theory, the LMN 93 result, named after Linial, Mansour, and Nisan, the three authors of the paper. And this basically showed low-degree Fourier concentration of classical AC0 circuits. And in order to be able to describe this result, I'll start off with some background on the AC0 circuit class, as well as classical analysis of Boolean functions. And once we've set up this background, I'll then move over to the quantum setting, where I'll describe a quantum class, which is very analogous to AC0, which we'll refer to as QAC0. as well as a quantum notion of analysis of Boolean functions. And using these two main tools, we will then be able to explain our result, which is in many ways analogous to LMN in terms of the key result statement, but the proof and idea that we use to get there is pretty different from the original LMN work. All right, so with that, I will get started, I guess, with this discussion of the classical LMN result. So to do so, I'll begin by describing this AC circuit class, which really is just the class of circuits that consists of alternating layers of and or operations. And we say that the size of an AC circuit is just the total number of gates in that circuit. And the depth is the number of these alternating layers of and or operations. When we put this zero superscript after AC, so when we call it AC0, we're simply referring to the subclass of all AC0 circuit or AC circuits, which has constant depth and polynomial size. Okay, so that's all I wanted to say for now about classical AC0. I'll now move into a brief discussion of classical analysis of Boolean functions for those who might not be familiar. And here, really, the key insight is that this set of parity functions, where basically given a set of input bits, you just multiply them. These parity functions form an orthonormal basis for all Boolean functions. And given this fact, we can actually define a Fourier transform. So given a Boolean function, we can decompose it into a linear combination over an orthonormal basis of these parity functions multiplied by a set of Fourier coefficients corresponding to each of these parity functions. So one example in the case that you have a function with two inputs is you could decompose, for example, some function f of x into this linear combination of 1 plus x1 plus x2 plus x1 times x2 multiplied by a Fourier coefficient of 1/2. We also have an important notion of degree, which for a given parity function is simply the size of the subset of the input bits that it operates on. And there's also this important theorem called Parsifal's theorem, which says that for a Boolean function, actually, if you take an inner product of the Boolean function with itself, this is equivalent to taking a sum of the Fourier coefficient squared. And this has the important property of always being equal to 1. Finally, we can define the notion of the Fourier weight specifically at a given degree k. So if we restrict our sum over all of these Fourier coefficients squared to those corresponding to terms of degree k, that's really all we're computing here. So to just give an example, if we were to look at the parity function, which has operates over all n input bits, and look at its weight, it would simply be a delta function concentrated at the maximal possible degree, n. All right, so now that we've seen AC0 and classical analysis of Boolean functions, we've set the stage to learn about this LMN 93 result. And so here, the key theorem statement is that if you're given an arbitrary Boolean function, f, that is computed by a depth d size s AC0 circuit, then it turns out for all degrees k, the weight that is greater than k has to be less than or equal to the size of the circuit times 2 to the minus k 1 over d. And while this equation might seem like there's a lot going on, importantly, what it implies is that if, for example, we wanted to approximate this parity function, which operates over all n bits in AC0, we would need that s has to be greater than or equal to k times 1 over d for essentially all k, which would imply that s has to be order of 2 to the n to 1 over d. But this is a contradiction since if you recall earlier, we defined AC0 to be the class of circuits of size polynomial in n for A. And this is starting to give a bit of intuition for how LMN was able to show a separation between the set of functions computed in AC0 and the parity function, which up until the LMN result had been kind of a long-standing question in classical complexity theory. To maybe offer a bit more intuition for this, what this function is saying is that if you were to take an arbitrary AC0 circuit and plot out its Fourier weight spectrum, it would look something like this, where you have most of the Fourier weight being concentrated on the low degrees, and then this tailing off effect for higher degrees. Meanwhile, as we saw earlier, the parity function is concentrated at the highest degree possible. And so this ends up implying a parity correlation bound, showing that parity is not actually computable by the class of AC0 circuits. Furthermore, because these AC0 circuits have this low degree concentration phenomenon in the Fourier spectrum, what this means is if you wanted to try and learn the output of an AC0 circuit, you could actually move into this Fourier domain and basically run a sampling algorithm that only looks at the log polynomial number of the smallest Fourier coefficients and sample from those to efficiently learn the AC0 circuit. And this was essentially how LMN were able to achieve the first quasi-polynomial learning algorithm for the AC0 circuit class. So now that I've gone through this important classical result, this really sets the stage to kind of foreshadow what we were able to obtain in our work. Most of our results at the end of the day were very similar to these LMN results, but just in the quantum setting. So to be concrete, following from this LMN result in the quantum setting, we were able to develop a new approach to quantum analysis of Boolean functions. We were able to derive a low degree concentration result for the quantum analog of AC0, QAC0. We were able to prove a parity correlation bound for the quantum parity function, establishing it's not in QAC0 for QAC0 with a restricted number of n bits. And we were able to propose the first quasi-polynomial learning algorithm for QAC0 circuits where we're only interested in one of the output qubits. That being said, there are still many important questions and challenges that remain in this work, and many of these derive from the fact that there are fundamental differences between the quantum and classical settings, and new challenges in this setting that make it different and maybe harder than the classical setting. Like we can't just directly move all the classical results into the quantum setting. So for example, we worked hard to try and prove tight bounds on the number of ancilla qubits, but we don't think we obtained the tightest bound possible. And obtaining tighter bounds on ancillas is still a very important open question in quantum complexity. Furthermore, all of these results, as I will explain in just a bit, are restricted to single output QAC0 circuits. And there's still this key question remaining of whether they could be extended to the case in which we have QAC0 circuits where we actually do care about all n of the output qubits. So with that, I will move on to the discussion of our work in the quantum setting. And to do so, I will begin by describing the QAC0 circuit class. And for this, I'll really start off by defining what we consider to be a quantum notion of AND. So we all know and love the classical AND function, which essentially says that for any input string, it'll output 1 if all of the inputs are 1, otherwise it will output 0. And so the quantum analog that we use in our work for this AND is the CZ gate operating on, for example, m input qubits. And the reason why we think this is a good analogy for and why the QAC0 class is traditionally defined in this way is if you look at the CZ function, it operates very similarly. If all of the input bits, qubits, are in the one state, it applies a negative phase to the state. Otherwise, the state remains unchanged. So really, this is just applying an AND operation in the power of the -1 phase. And so with this definition of a quantum AND, we can now define the QAC circuit class, which traditionally is defined as follows. You allow for an arbitrary number of single qubit rotation gates, as well as CZ gates of unbounded width. And we say that the size of a QAC circuit is the total number of gates, and the depth is really the number of layers of the CZ gates of arbitrary unbounded width. When we put the 0 subscript afterwards, it's the same as in the classical setting. We're restricting to the subclass of QAC circuits with constant depth and polynomial size. So one thing you might ask is whether the fan-out operation is contained in QAC0. And before I get into that, let me just start off by saying what the fan-out operation is. If you have one control wire, we define fan-out to be essentially the gate that, based on that single control, applies controlled knot to every other qubit or maybe a set of qubits. And so the question of whether QAC0 fan-out is in QAC0 is kind of a long-standing question in quantum complexity. It was actually originally first looked at by Moore in 1999. He was able to very straightforwardly show that QAC0 is contained in QAC0F or QAC0 with fan-out. But he asked this open question of whether QAC0 contains QAC0F, meaning whether fan-out is actually contained and computable in QAC0. Now, you might be wondering, why should we care if fan-out is in QAC0? It seems like a kind of random gate, but it turns out that there was this really interesting work in 2005, which showed that actually the quantum fan-out operation is extremely powerful. And if fan-out were to be in QAC0, this would mean that we could approximately compute functions like majority, sorting, arithmetic operations, phase estimation, even the quantum Fourier transform in constant depth. So this is a really important question in quantum complexity and quantum circuit lower bounds. And it's actually kind of very closely linked to the question of whether quantum parity is contained in QAC0, kind of analogous to this prior work we discussed in LMN, where they were able to show classical parity is not in AC0. And the quantum parity function simply acts very similarly to the classical parity function. Given a set of input bits, it maps the parity of those input bits into another register. And it turns out that with parity, we can actually very easily compute fan-out. So in particular, if you were given a circuit for computing quantum parity, if you were to apply a layer of Hadamard's before and after, you would get the fan-out circuit, and vice versa. So what this means is that if we can establish that parity is not in QAC0, this establishes that fan-out is not in QAC0, and we don't get all of this powerful computing function in QAC0, as well as an answer to this long-standing open question, which Moore posed. All right, so now that we've seen the QAC0 circuit class, I was going to move on to a brief discussion of quantum analysis of Boolean functions. So in this work, we are definitely not the first to look at quantum analysis of Boolean functions. This is something that people have been looking at in quantum computing for about a decade or so now. And one of the original works to really look at and introduce this notion of quantum analysis of Boolean functions was a paper by Montanar and Osborne from 2008. And really their key insight in proposing a notion of quantum analysis of Boolean functions was that these Pauli strings, which are just tensor products of Pauli matrices, form an orthonormal basis for any complex matrix with respect to this trace inner product. And so given this insight, similar to what we were able to do in the classical setting for Boolean functions, we can define a notion of a Fourier transform for unitaries, where given a unitary, we decompose it into a linear combination over these Pauli strings, as well as their Fourier coefficients, which we often call Pauli coefficients. And similar to the classical setting, we can define a notion of degree for these Pauli strings, which is simply the number of non-identity Pauli matrices contained in the string, or the number of qubits upon which it would act non-trivially, as well as the Pauli weight at degree k, which is simply the sum of all of those Pauli coefficients squared corresponding to Pauli strings of degree k. Okay, so even though Montanar and Osborne proposed this very nice definition of quantum analysis of Boolean functions, and there's been a lot of really nice follow-up work kind of building on their proposal and getting interesting results for things like, for example, Junta learning and more general channel learning. There are many challenges for quantum analysis of Boolean functions if it turns out if you're trying to develop an LMN type result. So in the classical setting, we saw that the notion of degree of a Boolean function was a pretty good proxy for the complexity of the function. So we saw in particular that increased degree had this correspondence with increased complexity. So classically, for example, the parity function, which operates on all n bits, had very high degree and was considered a pretty complex function. Whereas LMN were able to establish that most the functions computed by AC0 circuits actually concentrate on lower degrees, so they're not able to compute these very complex functions. However, what we see in moving to the quantum setting and trying to use this formulation of quantum analysis of Boolean functions by Montanar and Osborne is that unitary Pauli degree does not actually seem to be a good proxy or indication of circuit complexity. And to try and illustrate this, we came up with a very sort of simple example. So imagine you take the unitary that consists of basically just a tensor of X operations acting on every input qubit. If you were to look at the circuit depth of U, it is simply 1. So by our standards, this is a very simple quantum circuit. However, if you calculate the Pauli degree of this unitary, you actually get that it's degree n because you have an X operation acting on all n of the input qubits, which means that Pauli weight is actually concentrated at the maximal possible degree. And so if, for example, the quantum parity function turns out to also have degree n or some high degree, we can't really use this formulation of quantum analysis of Boolean functions to distinguish for example, this simple circuit from the quantum parity circuit. So clearly there seems to be some problem here, and it doesn't seem like we can straightforwardly use this original definition of quantum analysis of Boolean functions proposed by Montanar and Osborne to recreate the previously discussed LMN result in the quantum setting. And so that was really the starting point for our work and our proposal. So to give an outline of kind of the overarching flow of our work and what I will discuss in the remainder of my time here. So our work really began with a novel proposal for doing quantum analysis of Boolean functions. And with that novel proposal, we were able to derive a QAC0 concentration result very similar to that in the classical LMN work for AC0. Following from that QAC 0 concentration result, we then worked on developing a number of applications. One intrinsically quantum application was trying to develop tight bounds on ancillas. And as I mentioned earlier in the talk, we weren't able to get as tight of bounds as we would have hoped. So that's definitely an interesting direction for future work. We were able to prove some correlation bounds against parity and majority if you are working in a setting of restricted ancillas. And we were also able to develop a sample-efficient low-degree learning framework. Okay, so that's kind of the roadmap of where I'm headed. But for now, I'll just go back to discussing our kind of new proposal for doing quantum analysis of Boolean functions in order to be able to develop a result analogous to LMN. And so really the key insight in our new proposal for doing quantum analysis of Boolean function really started from this observation that, well, if you'll recall, the classical Boolean functions that we described previously in that LMN we're looking at are these functions that have only a single output qubit. However, quantum unitaries have many output qubits, all n of them. And we felt that this was an unfair comparison. If at the end of the day, we were trying to compute functions that are analogous to these classical Boolean functions in the quantum setting, where ultimately we really just care about one output qubit, we should instead perhaps restrict to just the single output qubit we care about. And so then the key question is, you might ask, is how do we actually restrict to a single output of an n-qubit unitary? And so for n-qubit unitary U, we considered in particular the quantum channel described as follows, where you essentially apply your circuit U, and then you're going to trace out n-1 of the qubits. And this is really just a mapping from n qubits to that one singular output qubit you care about. So intuitively, you can just think of this as taking our inputs, sticking them into our circuit U, and then at the end of the computation, discarding all of the qubits except for one output qubit. And for those of you who are familiar with tensor networks, the tensor network looks something like this. And in our paper, we have a few tensor network diagrams that I think help give intuition for some of our proofs and methods. But for the sake of the talk today, I won't really be using any of these tensor network diagrams. All right, so we've now defined a way to restrict our quantum circuit to just a single output channel, or to a single output qubit, by creating a quantum channel that traces out most of the qubits. But now we have this kind of complicated quantum channel, which is no longer really of the structure of a unitary on which we saw Montanaro and Osborne's definition for quantum analysis of Boolean functions. So the next question you might ask is, well, how can we actually perform quantum analysis of Boolean functions on these quantum channels? And the key way we were able to address this was actually by converting our channels into a state, which ultimately is just a complex matrix that has a decomposition in terms of these Pauli matrices or Pauli strings, as I described earlier. And so this conversion from a channel into a state is governed by the Choi-Jamilakowski isomorphism. For the sake of time, I don't think I will get into the details of all of this, but kind of the key thing that you need to know is that after taking your channel and plugging into this Choi-Jamilakowski isomorphism, you're left with this matrix phi, which is, at the end of the day, just a state matrix or a complex matrix upon which we can do this Pauli decomposition, where we now have a decomposition in terms of these Pauli strings multiplied by Pauli coefficients. And from this starting point, then we can use a lot of these quantum analysis of Boolean functions techniques as proposed by Montagnard and Osborne, and analogously to the classical setting. So with that, I'll now move into describing our QAC0 concentration result, and in particular, how we were able to prove a low degree concentration of QAC0 circuits using this new framework for doing quantum analysis of Boolean functions. So now that we've defined the Pauli spectrum of a single output QAC0 channel, we want to show that it is low degree concentrated. And what I mean by this is we want to show that the weight at degree k of this Troy representation matrix is less than or equal to epsilon for some low degree k and a very small epsilon. So again, we just want to show that most of the Pauli weight of this matrix is concentrated at low degrees. And so the proof that we ended up developing to show this can really be distilled into two main high-level ideas. So the first was that we were able to show that the weight actually depends on the number of qubits the channel acts non-trivially on. And for those of you who are familiar, this is very analogous to classical light cone argument. The second was that we were able to show that actually removing large CZs, so CZs which have a large number of input qubits, doesn't really affect the average circuit output. And this allowed us to eliminate large gates from our light cone. So this is really the high level gist of the argument, but I'll now go into describing each of these two steps in a bit more detail to maybe give some more intuition for what's going on. So in the first part of our proof was really just kind of a standard light cone argument. So you're given a QAC0 circuit C. You're going to use our mapping from this QAC0 circuit into a single output QAC0 channel by tracing out n-1 of the qubits. And then what you're going to do is from the single output qubit that's left remaining that you care about, you're going to work backwards and draw out what we call a light cone, where basically you just look at every single input qubit that's either directly connected to the output or connected to a gate, which is connected to the output qubit. And what this allows you to do is, at the end of the day, since all you care about is the singular output qubit, the only gates that are, and input qubits that are going to end up affecting it are the ones that lie in this light cone. So you can just delete eliminate all of the gates that lie outside of this light cone, drastically simplifying the circuit. So this is a very commonly used technique in proving quantum circuit lower bounds and in quantum complexity. However, it's typically used in settings where you're operating on circuits which have gates of constant width. However, in our setting, because as you can see, we allow for these really wide or large CZs, we still are going to have a pretty wide light cone. And so in our setting, it doesn't really seem to be as effective, which will lead into the second part of our proof. But kind of just to finish what I'm describing here, what we were able to show in our work is that if you can show that there's a subset of the n qubits, say, for example, L qubits, input qubits that lie in this light cone, then actually the weight of our Choi representation matrix at degree greater than L is going to be 0. So as I was saying, if we were in a setting where we had just constant width gates, we would essentially be done here because L would just be something on the order of 2 to the d, where d is a constant. So we would have something along the lines of weight greater than a constant degree is equal to 0. But in our case, because we have these large CZs, the number of qubits that are still in this light cone could be very big. And so this leads us to the second part of our proof, which is actually trying to find a way to remove these large CZ gates. And to give some intuition for how we were able to do this, I wanted to start off by mentioning that there is actually a quantum analog of this Parseval's equation that I had mentioned previously in the classical setting, where we saw that the inner product of two Boolean functions equal to the sum of the Fourier coefficient squared must be equal to 1. Well, in the quantum setting, if you want to get an expression that gives you the weight of your matrix or Troy representation, you have to look at the Frobenius norm of that matrix. And so what quantum Parseval is telling us is that this Frobenius norm, which, as we can see by the middle equation, is really just doing an averaging over classical input states, relates our matrix to it, or relates to the Pauli weight of the matrix. And so if we recall our definition of these extended CZ gates, what we saw earlier, right, is that for a given input, the CZ is really only going to do anything or if all of the input qubits are in the state 1. Otherwise, it will leave our state completely unchanged. And so intuitively, this means that the CZ gate is really only activating if all of the inputs are 1, which in this Frobenius norm setting, where we're doing an average over all 2 to the m or 2 to the n possible input states to the CZ circuit, means that our probability of the CZ activating is really only 1 over 2 to the m. And so this leads to the key insight that the larger the size of our CZ, or the more inputs to the CZ, the closer the CZ gate is to the identity in this Frobenius norm distance. And actually, for large enough number of input qubits or large enough size of our CZ, we can just replace the CZ with the identity operation for very little error. And this is really the key intuition behind removing large CZ gates in our work. So to go back to our light cone picture, we previously had this light cone corresponding to our QAC0 circuit. Now, if we were to take this intuition we just established and remove all of the CZs of large enough size, we would obtain some new, much simpler channel with a much smaller light cone, which, for example, has much fewer input qubits in the light cone. And our key result was that we were able to show that the distance between the Troy representation of the true original QAC0 circuit and now this QAC0 circuit with all these large CZ gates removed is actually less than or equal to k squared over 2 to the m, where m is the width of the smallest CZ we removed and k is the total number of CZs removed. So what this then means is you can, given a QAC0 circuit, calculate what error you're willing to allow and design it in such a way so that you can remove all of the large CZs and get a much simpler circuit out. And then this kind of led to our main theorem. So I'm just putting up on the slide the original LMN result to draw an analogy. But essentially our result, as you can see, obtained a very similar bound on the weight of these Troy representation matrices for a degree greater than k. If you look at the two equations side by side, you'll see that really the only difference that occurs is that we have a dependence on s squared, whereas LMN had a dependence just on s. We think this is because we used slightly different proof techniques. We used kind of like a triangle inequality and union bounding that might have been a bit loose. So we definitely think this s squared could probably be tightened to match the s in the LMN. And that might be another area of future work that could be interesting to look at. Okay, so to kind of summarize all of this, what this equation is now telling us is that similar to the LMN result of the classical setting for AC0 circuits, we were able to show that QAC0 circuits also have a low degree concentration phenomena. And so using this QAC0 concentration result, we can then start to look into applications in different settings. And I wanted to first just start off by talking about how we looked at and tried to get tight bounds on ancillas. So if you take our main theorem statement, one thing that I've kind of been sweeping under the rug this whole time is that we're only looking so far at QAC0 circuits, which we assume only have input qubits and don't actually have these extra ancilla qubits where they are constrained to be initialized to a zero state. We did look a bit at the distinction between dirty and clean ancillas, but for the sake of time, I won't get into that. If you're interested, it's all written up in our paper. But the interesting thing that we found was if we tried to extend our results to the case of ancillas, because as you recall, one of our main proof steps was kind of doing this averaging over a Frobenius norm, where we were kind of leveraging the fact that we were going to have many possible input states that we could average over. In the ancilla case, since these ancillas have a specified input qubit, this randomization argument starts to fail. And what we find is that we get a 2 to the A blow-up factor in our concentration result. So what this implies then is actually that our concentration result giving this kind of low degree concentration really only holds in the case that the number of ancillas is less than n to the power of 1 over d. So it really only works for a sublinear number of qubits. However, we conjecture that you might be able to reduce or eliminate this 2 to the A factor if you can be a bit more clever about handling these ancilla qubits. It's not really something we were personally able to make a lot of progress towards, but is definitely a very interesting direction for future work. And I think a lot of people in quantum complexity in the world of quantum circuit lower bounds would be very interested if something like this could be shown. In particular, I wanted to mention that this question of whether parity is or is not in QAC0 is really a longstanding open question in the quantum complexity community. A lot of people have worked very hard to kind of get tight bounds on the number of ancillas by which you can prove this. And we have a table in our paper that describes kind of all the prior work on this and compares our result to theirs. One thing that I wanted to note is that we do obtain the first average case bound where you are restricting to a sublinear number of ancilla qubits. I guess Greg Rosenthal also gave an average case bound, but his restriction was on the number of gates allowed in the circuit. And otherwise, most of the other bounds are worst case bounds, which are in principle weaker than an average case bound. So with that, I'll just move on to briefly describing our correlation bounds and sample efficient learning framework. So for the correlation bounds, we've now shown that for QAC0 circuits with the sublinear number of ancillas, we get this low degree concentration phenomena. If you plot the quantum parity function, it turns out it looks slightly different than the classical parity function. You have a lot of Fourier concentration happening at the highest degree n, but you also have this DC component at degree 0. I won't go into the details of why, it's just something you can calculate out. But at the end of the day, we see that quantum parity still has a lot of high degree Fourier concentration. And so leveraging our concentration result, we were basically able to show that if you were to try and run a QAC0 circuit to compute parity, and match the output of the QAC0 circuit with the actual parity function, what you would find is that their outputs would only match slightly more than 1/2 of the time. And what this really implies is that you're not much better off running QAC 0 than you are just simply flipping a coin or guessing the output. And so what this means is QAC 0 is bad at computing parity, and this is really how we get our correlation bound. The nice thing, though, is because we used Fourier analytic techniques, this approach isn't only constrained to working for parity, but also works for any high degree function you might be interested in, like majority or any other classical high degree function that you can map into the quantum setting. And again, we discuss ways to do this in our paper. And so lastly, I just wanted to conclude by discussing our sample-efficient low-degree learning framework. Again, the idea is very similar to LMN. Essentially, our result shows that most of the Fourier weight of these QAC 0 circuits is concentrated on polys of degree less than poly log n. So if we define K star to be the maximal such degree of which you get this concentration, it turns out that by sampling the Fourier coefficients of terms of degree K star or less, you can actually get a very good approximation to the true Troy representation of your QAC 0 circuit. And in our paper, we spent a bit of time describing actually 2 different procedures for extracting these coefficients. One was just kind of standard Troy state tomography, where you just run classical shadow tomography directly on a physical implementation of this Troy representation, which we call a Troy state. The problem with this is creating a Troy state and running this Troy-Jamilakowski isomorphism requires you creating a lot of Bell states. So it wouldn't be super practical in an actual lab setting. So we spend a bit of time also describing a slightly less sample efficient procedure, but still very similar efficiency that avoids having to actually create Bell pairs and just involves directly querying the channel with an input and measuring the output. And so this was how we were able to obtain the first quasi-polynomial learning algorithm for single output QAC 0 circuits. And so I just have, I wanted to conclude with our table of kind of our key results from our paper. So analogous to the LMN result for AC 0 circuits in the classical setting, we developed a result for QAC 0 circuits in the quantum setting. We used Pauli tensors as our Fourier basis. We came up with a new proposal of quantum analysis of Boolean functions, where again, we were looking at the Pauli decomposition of the Troy representations corresponding to a channel, which restricts to just a single output of our QAC 0 circuit. We obtained the first QAC 0 concentration result, very analogous to the LMN one for AC 0. We proved the first average case QAC 0 bound for a sublinear number of ancillas, and we gave the first efficient learning algorithm for single output QAC 0 circuits. So that's it for my talk. Thank you all for listening, and I'm happy to take any questions.